I welcome all of you to my stage show, and I should mention that I am very much honored for getting this opportunity to do the inaugural Khandelwal Science Stage. And it was been named after Khandelwal because I have met Khandelwal and I know how much he was aspiring about the physics teaching. And maybe because of him, today I am going all over India to do stage shows. I shall present today few activities on the simplest concept of light or optics, usually called visible light. I shall prefer to name my performance as seeing is believing, because when we see something, we really believe it that this has happened. So, the importance of showing activity to the student lies in the fact that students themselves, when see the activity, first they believe that phenomena actually happens. And they do understand the underlying concept without much explanation. And not only they learn, but also they replicate the activities and enjoy. Today we are going to have a lecture on optics. Optics means the light, with the help of that we can see objects, that means it is called visible light. But one thing you must remember, visible light means as if you can see the light, the electromagnetic wave of which there is a portion which is called visible light. Actually that light cannot be seen. We cannot see light. This is very important, that visible light, it means that light by which we can see, but that particular light we cannot see. Let us check with some example. I have a laser torch over here. You see that I am going to shine this laser on this screen. You cannot see the path of the light. The laser is on here, the light is falling here, and we can see the spot only, but we cannot see the path of the light. That means light is invisible, but when light falls on some object or something, light get diffused, reflected from there, and therefore we can see the object but not the light. But we are going to show you that how light really travel in a straight line. Now what I do, if you come over here, I have some chalk dust, and you can take the chalk dust in your hand. Now I have make the arrangement complete. Now you start clapping like this. When you clap, the chalk dust goes in the air, and those dust particle when falls on this, each particle is scattering the light which is falling on them. So now we have another point, another word which is called scattering. Previously we have seen that we talked about the rectilinear propagation of light. In this experiment we shall see by ourselves that this light is really traveling in a straight line. Wonderful. But this scattering, what is scattering? Scattering is something that when light falls on small particles, they absorb the light and then they re-emit in all directions. Now, when laser falls on a particle, that particle absorbs energy and this energy is scattered in all directions. And this scattering also depends on some factor, though in your book it is not given. There is a scattering factor alpha, which depends on the thickness of or the particle size, its volume, wavelength of light, and there is a 2 factor over here. This is called scattering factor. So, this scattering factor alpha is given by this. So, you can see if the particle is larger, then lambda has to be larger. But I know that as a preliminary lecture, if I talk about lambda, particle size, scattering, you won't be able to understand. Let us get down to a lower concept. What is that? In this experiment, you see that mirror always has 2 layers and the mirroring is actually behind this. So, when laser light falls here, light normally gets reflected from the upper surface and a portion of this goes down to the lower surface and actual reflection takes place in the lower surface. So, from the lower surface reflected light goes and it transmitted parallelly to the first ray. So, this is the second one, this is first ray, this is second ray. Again from here there is another ray goes down from the upper surface and again it goes to this level and it starts going in this direction. But obviously, the second one which is getting reflected from a mirror surface is maximum intense. So, when you look at this beam, the beam which is being reflected, you can see that the second or central one is the strongest one and this part, this is weak. Now, here is a combination. If I switch off it, gradually the lights will go on and you will find that inside this practically no light is seen and as if it is a black box, nothing is inside. But if I on this light, then you can see that a large number of images are coming one after another. Whatever I have used in this box is a normal LED which is previously available, they are not that intense. Nowadays, very intense LEDs are available. If I put the strong LEDs inside, then you would have seen a long veil as if that is an infinite veil. What I have done, at the back there is a mirror and at the front there is a colored glass which permits partially. So, as it permits partially, some part is reflected back and some part is refracted out. Actually, in a jewellery shop, when you go, you will see both the walls have mirrors and you can see your infinite number of images in either of the wall. We have discussed about the scattering of light. Now, there is a wonderful experiment on the scattering, particularly the Rayleigh scattering, because you know that in the morning and in the evening, the sun when rises or sets, it becomes reddish and also the sky is blue. For that, we have arranged an experiment. There is a glass box in which there is a liquid and from the left there is a torch light which is passing through that liquid and it falls on a screen on a table and you can see there is a reflected image below because the table is made of glass. Now we pour some liquid which is actually very dilute hydrochloric acid. Let me see, the solution in the glass box is the very dilute solution of sodium thiosulfate. Now as the time passes, if we look carefully in the liquid of the box, then we will find it is becoming very light blue and gradually this blue increases. And if we go to see the patch of light on the screen, that also changing little bit of color. Now, still more, if more time passes, then we see the blue color gradually becoming whitish. That is because this is no longer a Rayleigh scattering, but this has become Mie scattering. That means when the particle size increases, then the color effect goes. But because of the smaller particle throughout the length, we can see that the patch of light is gradually becoming orangish and towards red. And particularly the lower part where there is the reflected part, it exactly looks like a setting sun. Now, if still more time is given, then we shall see that that light, the patch of the light on the screen is gradually becoming reddish and gradually intensity becomes very low and as if the sun has set on the western sky. Let us now see the utility of the two eyes. Why we have two eyes? What is the advantage? Here we can see a lady is sitting with one of her eyes closed and someone is proceeding with a pen and there is a glass on the table. So he is asking at what position he should drop the pen within the glass. And that lady was saying that please come forward. And when it is dropped, it is seen that it is placed out of the glass. Then with the second eye, the other eye, the lady was asked to close the other eye and then the pen was taken from the front. Initially she said that you take towards me, then she corrected and again the same thing happens because when she said drop the pen, the pen was outside the glass. This very clearly proves that the two eye help us to estimate the distance or it gives the 3D perception of a view. Now we are going to create a narrow beam of light for reflection experiment. We can see that a narrow beam is coming out of a torch where there is a slit cut, but the light which will come out, it is a cylindrical wavefront. So to eliminate the sidewise light, we place two blocks of wood. So finally we see the very narrow beam has emitted. Now where we see the cross, actually at that point there is a very thin mirror and in the mirror you can see the image of the torch. Now on the figure on the left hand side I take a pencil and put marking on the left side of this beam and also the reflected beam on the left side. Now if we rotate the mirror keeping the position of incidence same, then the position of the reflected ray will change. So here, though it is not being shown, I have taken 3 positions of the mirrors and that has been recorded on a piece of white paper. And from there we have seen that the angle of incidence is equal to angle of reflection and also the amount of rotation of the mirror is half of that rotation of the reflected beam and obviously all the rays are on the plane of the paper. In this picture we see that a scale is placed in front of a mirror on a graph paper. Both from the scale or from the graph paper, if we measure and if we estimate the sizes, we shall see the sizes of the centimeters, they are all equal and the object distance is equal to image distance, which is indicated by another piece of paper which is placed with the scale. Now I am going to show you 3 pictures of lateral inversion. All of you have seen the pictures in the book, but here you see the first picture is showing that there is no lateral inversion, though there is written physics and behind that there is a mirror. In the second picture you can see there is a lateral inversion where the physics is written which is placed perpendicular to the mirror and it is laterally inverted. And in the third picture, you both see the uninverted image and also the laterally inverted image. I am not going to explain it thoroughly. I expect that all of you should think about it and find out the reason why this thing is happening. Refraction. But actually, along with the refraction, there will be always some reflection and also some absorption. Now you can see my apparatus contains a ordinary previously we have the filament clamp. I have removed the filament. This bulb itself is my apparatus. Now if I pass the laser light through it, through air it will go in a straight line, through water it will go straight line, and we can reflect, refract, everything can be seen. I am going to show you after this that how laser light is being reflected and refracted simultaneously, and also the total internal reflection. Now you see, this is light is traveling in a straight line in air, and light is also traveling in water, so in a straight line. So you see, any particular medium light always travels in straight line. Now if we pass on from the rarer to the denser medium, which we were just discussing, you can see clearly that a part of the light is reflected and part of the light is refracted. Now if I increase the angle of incidence, the intensity of the reflected beam increases and the refracted beam also decreases. This is a very important law of refraction of light, that when the angle is more or less perpendicular, reflected line becomes weak and the refracted line becomes strong. So from this experiment we can see that when light gets reflected from a boundary, a part is refracted and a part is reflected. But as the angle of incidence increases, you see the reflected intensity is more than the refractive intensity. Now if we go from water to air, what will happen? Let us see. And you see that the light goes straight. Now I gradually increase the angle of incidence. See, in water also you can see a part is getting reflected. In the water also a part is getting, as the angle increases, the reflected intensity in water increases. Now there is no reflected intensity almost. Refracted intensity is strong, but now the reflected intensity is increasing. If I increase the angle more, then you see there is no refraction. This phenomena is called total internal reflection. That means when light travels from a denser medium to a rarer medium, when the angle of refraction just exceeds the 90 degree, angle of refraction exceeds the 90 degree, then it totally reflected in the first medium. So this is total internal reflection. And if we continue to go further, it is always total internal reflection, and again we come to the rarer medium to denser medium. Here you don't get total internal reflection. That means in total internal reflection always occurs when a particular angle is exceeded. That means the angle of refraction becomes 90 degrees. Now again I just tell certain things, that when ray of light refracted, this is medium 1 and this is medium 2, whatever we find out that this is angle of incidence, this is angle of refraction, then this refractive index mu is normally, it is the refractive index of the second medium with respect to the first. The ray of light will now go from the denser medium to the rarer medium. So this relation we can change it in this way, that instead of mu 2 1 we can also write it is mu 2 by mu 1. And if this angle is theta 2 and this angle is theta 1, then mu 2 by mu 1, that means this reverse relation will be sin theta 1 divided by sin theta 2. This is the most general formula, that means we can write mu 2 sin theta 2 is equal to mu 1 sin theta 1. Now, in case of water, if the refractive index of water is mu w and the angle now becomes the critical angle theta c, then you see it will be sin theta c, and for air if you consider the refractive index is 1 and sin 90, because in this case when it is the falling at critical angle it traces the surface, that means angle of refraction is 90. So, now we get refractive index of the first medium is 1 upon sin theta c. By this way, if we know the critical angle from such experiment, then we can find out the refractive index. But I tell you, for the class 9 or class 10 students, I do not think this relation is there, but if it is in your syllabus, better you remember this formula. This is the most general formula for refraction between two medium. Okay, thank you. Natural and beautiful phenomena, and we see in the sky that beautiful rainbow forms, and the primary rainbow has a color red on the top and blue below. To explain this rainbow, in most of the books it is said that when light enters the single water droplet, that is being refracted first on the top, then they reflected and then again refracted in the other side. But here most of the book says that it is a total internal reflection. That is not the case. I am saying because if you calculate the critical angle for water to air for say red, then the angle will be about 49 degree. But when a rainbow is formed, all of us know that the between 41 to 42 we see the rainbow. When a person is standing on the ground, they see it, that is why it is so. But before that, let me tell you that from I and R we can find the relation between them from Snell's law. If you put a value of I, then R can be calculated, and from the geometry of the rays you can calculate that the incident ray and the emergent ray, if that deviation is delta, that is given by 4R minus 2I, that is in the fourth line you can see. Now, we see what we can calculate, that we calculate the incident, reflected angle of reflection, and then the deviation. Let us go to the next slide. We have calculated I, R and delta for red and also for blue, and you see if the angle of incidence gradually increases, I have written here from 30 to 62, you see at 59 degree the delta is maximum. That means red light at 42.36 it will come back, because after that if the incidence angle increases, the deflection of the red light does not increase. So, that is the maximum limit of red. And for blue similarly we can see that at 59 degree incidence it becomes 41.07. That means blue color comes below red. So, we see that none of this red or blue, they are totally internal reflected, but they are simply reflected, and that reflection is the maximum angle. So, in this picture we see that above the red line, which is from the eye, a person who is looking from the ground, the angle of the red curve is 42.4 degree approximately, and above that there is no light, and red is everywhere below that, because for all the colors red is reflected from that, but the intensity varies,
accordingly. Similarly, violet light, the maximum spread of the violet is 41. So, below 41, red, violet and all other colors are superimposed on them. So, we get a very bright whitish region. But above the rainbow, we say dark region. If you look at the rainbow very carefully, then we will see that character, and we can do experiment. But in any case, because of the shortage of time, I think I can give you the rainbow. Everybody has seen that primary rainbow has red above and the blue below. But I request all of you, look at the rainbow and see the dark region above the rainbow and the bright region within the rainbow, and the total internal reflection concept is not correct. Thank you very much.